All right, let's take a look at section 15.4, which will cover double integrals in polar coordinates. So just the one learning objective this time, which will be calculating double integrals using polar coordinates. And here on this page as well, I've provided the equations that'll convert us between rectangular coordinates and polar coordinates. So the easiest are just the x equals r cosine theta and y equals r sine theta. But we'll probably also want to be using the other two equations as well, which are x squared plus y squared is equal to r squared, and also y over x is equal to tangent theta. Polar rectangles. This is just to kind of give us an idea of what shapes are going to be easiest to integrate in polar coordinates rather than in rectangular coordinates. And those are going to be the shapes that have some kind of a circle shape to them. So we define a polar rectangle to be any region given polar coordinates r and theta, where r exists between two constant numbers. We'll think of r as the radius. And we'll also want theta to be between a couple of angles. And we're going to say that we specifically want these polar rectangles to only happen where a and b are both positive. And we'll also have just b be the larger of those two, a positive or 0, I suppose. We're fine if a is equal to 0. And also that we want the difference between our two angles to be less than 2 pi. Meaning that we don't want a polar rectangle to wrap around itself. We'll just want to be either a full circle or less than a full circle. We also don't want to go below 0, so we'll just make sure that beta is always the larger of our two angles. A few examples of what those polar shapes look like are shown here. So a circle that is completely filled in, we'll consider that to be a polar rectangle. Really just means it's a shape that's very easy to integrate in polar coordinates. In the second figure there, we have only the top half of a circle with also an interior circle cut out of it. Still would be a shape that's particularly easy to integrate in polar coordinates, and a couple other shapes off to the right as well. But before we move on to our next theorem, let's talk for a moment about what dA really represents. So we talked a few sections ago about dx being an infinitesimal change in the x direction, and dy being that infinitesimal change in the y direction. And so dA should just be an infinitesimal, really small change in the area. It has already made sense to just use dx times dy to talk about dA when we were integrating rectangles. Because if we multiply those two pieces together, we should get just a small change in area rather than just a small change in either direction if we just took dx or dy by itself. So if we look at each of dx and dy, both of those are going to have a dimension of 1, since they just measure the change in a single direction, in the x direction for dx, the y direction for dy. So the product of dx and dy will give us a dimension of 2, which is exactly what we want for the area, because the dA should have a dimension of 2 since it's measuring an area. But let's look at what happens if we look at dr and d theta. So dr should just be an infinitesimal change in the r direction. So we'll have to take into consideration where our point is in space, but then it should just go out in the direction of the origin. Right? If we just connect our point to the origin, dr should just continue going in that direction. So if we put dr up here on our little chart where we're measuring our dimensions, dr should also have a dimension of 1, just in the r direction. But theta is a little bit weird, since if we consider for a moment what the angle actually is, it's just a measure of, well, it's the angle between two lines. And an angle doesn't particularly have a dimension, since it would not matter where along those two lines I'm measuring the angle, that angle theta should always be the same. So theta is kind of, well, theta is dimensionless, so it should have a dimension of 0. So if we were to look at d theta and where we'd want to put it on this diagram, I've drawn in let's call it a unit circle that I've drawn in over by the origin. But the unit circle doesn't exist in the same space necessarily as all of our other x, y, and r values, because that unit circle is sort of designed to be a dimensionless circle. So d theta is going to have a dimension of 0. Also, d theta isn't located at the point that we're trying to measure out in space. It's, again, on this sort of theoretical unit circle. So if we took the product of dr and d theta, we'd only end up with a dimension of 1, which isn't going to match up with the dimension that we know our dA needs to have. So instead of using just d theta, which only would talk about the change in an angle, but not necessarily how our point is changing through space, we'll want some other value shown up here in green. Right? I want to talk about how that point changes through space. And I know it needs to be related to d theta, but if I want to move d theta from the dimensionless unit circle that it's being measured in out to the point that we're actually in, I'll want to take d theta and multiply it by r. So that r times d theta would give us that green arrow that we've drawn in that actually exists where our point is. That way, if we throw r d theta up here on our dimension tracker, r d theta should have it a dimension of 1 now. Since r is dimension 1 but d theta is dimension 0, that product should come out to a dimension of 1. Meaning that if I want to get that dA, the infinitesimal change in the area where our point is in polar coordinates, I'll want to multiply dr, which is the one that just makes sense, by r d theta. So that we end up actually tracking how our point changes through space, rather than just looking at how r would change through space. So dA looks a little bit different when we're in polar coordinates. Instead of getting to be just, in rectangular coordinates, it's dx dy. In polar coordinates, it does not get to be just dr d theta, because again, we wouldn't match up with our dimensions. So instead, dA is going to come out to, usually it's just abbreviated r times dr d theta. But the point of this exercise is to show that r that we're going to have to multiply in for dA is really attached to the d theta. That's the part that it's coming from. So practically speaking, what that means is that every time we do a double integral in polar coordinates, we're going to need to multiply our function by r because of that dA factor. So if we bring that into the theorem, where again, we'll use the fact that dA is dr times r d theta, or most often just abbreviated r dr d theta. It's important to pay attention that this r right there is coming from dA. But that means that our polar double integral looks just like the iterated integrals we've been doing before, with the one addition of that r that we're going to have to multiply in. Okay, so let's actually look at an example where we'll go through that. So we'll evaluate the double integral of e to the negative x squared minus y squared dx dy, where r is the region between x equals 0 and x equals the square root of 4 minus y squared. So hopefully we recognize that second equation as the right half of a circle of radius 2. So that's what I've drawn in the diagram on the left. We'll also need to get our theta boundaries, since if we know that that's a half circle of radius 2, r should bounce between 0 and 2, but our theta needs to go between straight down and straight up, which if we're going in standard position, straight down would be an angle of negative pi over 2 or 3 pi over 2, but we're going to use negative pi over 2 so that we can have a continuous region. And straight up is an angle of pi over 2. Meaning that if we look at our double integral over here, or our iterated integral that we're changing into, theta, we want to go from negative pi over 2 to positive pi over 2, while r goes from 0 to 2. Plug in our function, which will be e to the negative r squared times dA, which is where we need to multiply by r times dr d theta. Dr d theta. And let's highlight that r in red, since I highlighted in red in the example above. So make sure that we remember to multiply that factor of r because of our dA. Right, so let's start integrating. Because we multiplied in by that r, that e to the negative r squared integral becomes quite a bit easier since we can make a u substitution. So let's get that done. This ought to look like the integral from negative pi over 2 to pi over 2, because we're going to do r first, of 1/2 e to the negative r squared, that evaluated from 0 to 2, still times d theta. And if we actually plug all that stuff in, we'll get 1/2. Well, let's keep that going. We still have the integral part here. 1/2 times e to the negative 4 minus e to the 0, which is 1. Put our d theta in, still going from negative pi over 2 to pi over 2. And then doing the theta integration. There is no theta that we have to integrate, so it'll just be integrating d theta would go to theta. We'll plug in pi over 2, plug in negative pi over 2, take the difference between those, and we should end up with just pi. So pi times 1/2 becomes pi over 2 times e to the negative 4 minus 1. All right, taking a look at example 2, we want to convert this rectangular integral into a set of polar integrals where we've got y going in between the functions y equals x and the function square root of 2 minus x squared, with x being between 0 and 1. So hopefully we recognize that top equation for y as a circle with a radius of the square root of 2. Since the square root of 2 minus x squared, it should have been square root of r squared minus x squared. So the radius will be square root 2. So that means that our r value should be between 0 and square root 2. 0 and the square root of 2 for r. Getting theta is going to be a little bit different. Notice that since we were integrating x second, y equals x should be the bottom function, with y equals the square root of 2 minus x squared as the top function. So we want that slice that is adjacent to the y-axis. It's highlighted in green. But we're going to need to figure out what our angle theta should be. So I'm going to start with the equation y equals x, which is the one that is our lower bound. And we'll change that over by dividing both sides by x. We get y over x is equal to 1. And we also know that y over x is equal to tangent theta. So the line y equals x is the same polar equation as tangent theta equals 1, which if we just solve that for theta, it should be theta equals pi over 4. So if we go counterclockwise, which would be our standard orientation for theta, that means that we will start our theta integral at pi over 4 and end up at pi over 2, since that would be straight up, going from 0 to 1 along the x values. So we might as well also fill in 0 and square root of 2 for our r values. And we'll change x and y into r cosine theta and r sine theta. So x plus 2y will be r cosine theta plus 2r sine theta, as has already been written out. And we'll want to change over our dA as well. So instead of dy dx, we'll want r times dr d theta. It looks like we're doing dr first, since that's what's set up on the inside. Then if we go to integrate that r with our r values first, looks like we can factor an r squared out of the whole piece, meaning we'll have r squared times cosine plus 2 sine. And integrating r squared would give us r cubed over 3. We're evaluating that from 0 to square root of 2. I'll also fill in the leftover theta pieces. So we do that down in the next line as well. But if we evaluate r cubed at 0 and at square root of 2, at square root of 2, that'll be 2 to the 3 halves power, and at 0, it's just 0, so that will simplify to 2 to the 3 halves over 3, or the square root of 8 over 3. It's the step we'll take in simplifying down in the next line. Next, we'll need to integrate our theta components. So cosine integrates to positive sine, plus 2 sine integrates to negative 2 cosine theta. So we'll fill in those, and then also we're evaluating that from pi over 4 up to pi over 2. So as our last step, we'll plug those values in. Sine of pi over 2 is 1 minus 2 times cosine of pi over 2, which is 0. And then we'll subtract from that the sine of pi over 4, which is root 2 over 2, minus a negative 2 times the cosine of pi over 4, which is also root 2 over 2. So in the end, we can simplify this a little bit. We've got the square root of 8 over 3 times, looks like 1 plus root 2 over 2. And let's call that good enough. All right, and finally, our third example, we'll find the volume of the solid bounded by the plane z equals 0, and the paraboloid z equals 1 minus x squared minus y squared. So if we look at what that region is gonna, that two-dimensional region that's in the xy plane is gonna look like, that'll be what happens if we set our equations equal to each other. So 0 equals z, and z equals 1 minus x squared minus y squared. which if we rearrange that equation, we should get x squared plus y squared equals 1. So we're looking at a circle of radius 1, meaning that r is in between 0 and 1, and theta is in between 0 and 2 pi, because we're going to want to go all the way around this circle. So plug all that stuff in. We're going to be looking at the iterated integral of 0 to 2 pi and 0 to 1 of nope, let's try that one more time. That's the first example. We just want to integrate our paraboloid. So we're going to integrate the function 1 minus x squared minus y squared, which is really 1 minus r squared. Multiply that by r times dr d theta. Right, since our integrand has no dependence on theta, if we just do, that means we could do that separation of integrals pieces that we talked about a few sections ago, separate it out into a single integral that depends only on theta and a single integral that depends only on r. And that theta integral is just going to integrate out to 2 pi, since we're going from 0 to 2 pi. So that'll be 2 pi times the rest of the integral. We're integrating r minus r cubed, since we had to multiply that r in. So we're looking at r squared over 2 minus r to the 4th over 4, if we integrate each of r and r cubed. And that thing's got to be evaluated from 0 to 1. So we've got 2 pi times 1/2 minus 1/4 minus 0 minus 0. 1/2 minus 1/4 is going to be 1/4. And 1/4 times 2 pi is pi over 2. So that should be the volume of that paraboloid, the volume of the solid bounded by the paraboloid, and the plane t equals 0.